two-part video. The first part, we're going to look at vertical asymptotes and holes, and the second part, we'll look at horizontal asymptote. So what we've done so far is we've looked at functions like y equal to 2. That's a constant function. The graph would look something like this. Y equal to 2 would be a flat horizontal line, y equal to 2. And if we make it a constant, it could slide anywhere we want here, -2, +2, 7, 4/3, whatever. That's one function we looked at. Then we looked at y equal to mx plus b, and that's was familiar to us as well. It was a diagonal line, and that could be moved up and down, or it could be positive or negative. And so we handled those. Then we got to y equal to a x minus c squared plus d, or b squared plus c, and that's just your parabola. And your quadratic or parabola is going to be able to move up and down. We looked at the quadratic formula, and if b squared minus 4ac was 0, it was touching somewhere along here on the x-axis. If it was less than 0, it didn't touch. If it was greater than 0, it touched in two places, so we had two roots. So we handled that, and you could also have that upside down as well, moving up and down if a was negative. Then we looked at polynomials, and polynomials were degree 1, like linear on up. All of those were integer powers, and we did 3, but we could go 3, 4, 5. Those were polynomials, and that's where we got into the idea of several zeros, finding zeros using synthetic or using long division, and that helped us find the zeros. And once we knew the zeros and the multiplicities, we could sketch those from our leading term. And the leading term told us, in this case, it's an odd that one side is up, going to infinity, one side's down, going to negative infinity. If it was an even power, they'd both be going up or both be going down. So that leads us to this chapter, which is y is equal to something that might have a polynomial in the top, and then in the bottom might have some kind of a x minus g, some kind of a constant there. And so let's say it was a 2, x minus 2. Well, if there's an x minus 2, weird things start to happen. We get vertical asymptotes, we might have things cancel out and get a hole. We might be able to have a horizontal asymptote, maybe we don't. So this is what we're doing this chapter, going from those other functions. So let's talk about rational functions. A rational function has a function like a polynomial with x in it in the numerator and a polynomial with x in it in the denominator. And this is where we start to get these interesting looking asymptotes. We get, you can see the vertical ones I just drew, and these would be the horizontal. So if you have the purple ones are vertical, the green one is a horizontal asymptote. And we're going to find out how to actually figure those out and calculate those. And I'm going to launch right into it. If you take number 1 here, it has 2x minus 1 over x plus 1. Well, f of x is equal to 2x minus 1, x plus 1. Well, let's look at the domain of this. The domain is going to be all x values, but there's one that's going to be all real numbers, but we can't have one value, and what that value is -1, because then it'll be undefined. Some people will write it negative infinity to negative 1 union, negative 1 to infinity. That's fine too. But what that would look like would be some kind of a graph with x equal to negative 1 as a vertical line that the curve doesn't get to. And I would guess that this one might look something like this. Okay, so this is how we find the vertical asymptote. We set denominator equal to 0. So in this case, x plus 1 equals 0. X equal negative 1 is the equation for the vertical asymptote. That's how you do it. No big deal. Not too hard. Other ones, let's try this number 2 here. Number 2 says g of x is equal to 2 minus 3 over x plus 1. Well, whenever we deal with fractions, we like to have the same denominator. So we can multiply by 1, x plus 1 over x plus 1. And that's just going to give us 2x plus 2 minus 3, which is 2x minus 1, all over x plus 1. And as it turns out, that's the same as what we just had, which is kind of cool. So that's a start to vertical asymptotes. Another thing you need to know about vertical asymptotes is we can take limits. So do you remember when we had something like this, the function went like this, we said the limit as x goes to infinity, right? Infinity of your function f of x. This one is going up, 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 up to positive infinity land. There you go, positive infinity. With this one, we'd say the limit as x goes to negative infinity this time to negative infinity, that y value is going to go to down, 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 downtown to negative infinity. So again, the way we group these is you write limit, and then below it you go what x is approaching, and then side by side with limit you go what's the y doing. The f of x equals the y value negative infinity. On this side, x goes to positive infinity, the y goes to positive infinity. So that's what we had before. But now what we're going to do is we're going to be using these vertical asymptotes. And with the vertical asymptote that might be here, for example, let's say this is the value x equals c. The graph could do something like this. And now what we could say is the limit as x approaches c from the, now this is going to be left, c with a negative sign on this side. Now this is negative c. Oh, excuse me. I said one thing and I did another. Okay. This is negative c, and this is c from the left. Okay? So we would put the little negative here. It looks weird, but that just means c from the left. If it was on the other side, it'd be negative. And then you would say the same thing, f of x, and what is it doing? Well, it's going to positive infinity. So we have the same thing. X is approaching c. Here's my x value c. From the left, it has a little minus sign there, and it's going up, 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 up. But if you look at this one down here, the limit as x approaches c from the right, and again, this would be positive c. This would be c from the other side, the plus side or the right side. This would be positive, and right. So they're different. And then f of x is equal to, This one's going down to negative infinity. So there's my y's, and here's what's happening with my x's. It's not very hard to write. You just have to kind of get used to it. So that's the nomenclature for vertical asymptotes. We could have horizontal asymptotes. Horizontal asymptotes are going to look something like this. So here's your line, and this is your asymptote. Let's say y equal to d. And let's say my curve is doing something like this, okay? And maybe on this side, yeah, that's fine. Goes something like that. Well, what we're seeing here is that the limit as x goes to infinity, positive infinity, of f of x is not infinity this time. As we go to infinity, it looks like it's going to y equal to d. So a little bit different. You have x approaches infinity, and then the y is approaching d. So that's your horizontal asymptote. All right, well, let's see if we can deal with we'll find horizontal asymptotes in a little bit on part 2, but for this one, we're just going to practice finding vertical asymptotes and something called holes. So if you look at this first one, we could rewrite it as 2x over x plus the square root of 3 and x minus the square root of 3. And we notice that x plus root of 3, x minus root of 3, there's nothing to cancel out. So we're going to have two vertical asymptotes. One at, and then you just say x plus root of 3 is your factor, set it to 0, x equal negative root of 3. And do the same with the other one, and that'll just be x equal to positive root of 3. These are vertical equations. Y equals a vertical line, and those are your vertical asymptotes. Now, nothing cancels, so we call these non-removable. It seems weird, but that's what it is. Now, take a look at this number 2. Now you have g of x is equal to x minus 3, x plus 2, over x minus 3 times x plus 3. Now you're going to notice there's two places where the domain isn't going to work. The domain is going to be all reals, and it's not going to be 3, and it's not going to be negative 3. But something happens with these 3's. The 3's are going to cancel, and so we call this removable because they remove from the equation. But they're still there. It's still undefined at negative or at positive 3. Now, how can that be? Well, what happens is that this graph just acts like it's not there. At 3, it's going to act like it's not there, but we put what we call a hole at that spot. And what the hole does is only at that value, x equal to 3, is that value not defined. So you can't put a 3 in and make this work. But if you look at the graph, this graph is going to be infinitely close to itself to making a perfect curved line. And you can think about this, if there's one point out of an infinite number of points, is that hole there? Very arguable. But we'll draw a big circle there, even though it's infinitely small, where you can't put in a 3. But then what happens with this x plus 3? Well, that's going to be a vertical asymptote at x equal to negative 3. And a hole at x equal to 3. Because the hole canceled out, it's removable, and this negative 3 doesn't cancel out, so it's non-removable. Okay? And then, you know, we get situations like this number 3, where you're going to have x minus 3, x plus 2, over x squared plus 9. Now notice that this x squared plus 9, that has no answer. So since it has no answer, there will be no holes and no vertical asymptotes. Okay, so that's it for part 1. Go to part 2 and look at horizontal asymptotes.